Hello again, and let's see now some options or variations of the backpropagation algorithm. So some heuristics for making backpropagation better. So training with backpropagation used to be more of an art than science. But so it used to be based on one's own experience. But now with meta learning and tools such as TensorFlow and PyTorch, they make life much easier. So one of the things you need to do before you start your training using backpropagation is to normalize your inputs. So you pre-process your input so that the mean value is closer to zero or equal to zero. So you can look for this function, for example, in MATLAB. And the input variables also should be uncorrelated, sorry. So in that case, you can use tools like the principal component analysis and functions like this to make your input variables or the input patterns uncorrelated. There are two ways of on how to on training your backpropagation or training using your backpropagation. The first one is the sequential mode, and the second one is the batch mode. So in the sequential mode, learning means that a given input pattern is forward propagated, just like what we've shown before. And you determine the error and you backpropagate that error, and then you update the weights. And then you do the same thing for the next pattern. And then the third pattern, fourth pattern, and so on. So you do the training or the weight update, you do it in a sequential manner, meaning at every time you input a pattern to your network or to your multi-layer perceptron in this case. As opposed to the batch mode, where learning means that the weights are updated only after the entire set of training patterns has been presented to the network. So for example, you do it, you do for one epoch. So in other words, all patterns are forward propagated, just like before. You determine the error, you propagate, but then you don't update the weights. So the weights are only updated when all patterns have been processed, meaning what? That the weight update is only performed every epoch. So you do for you do the update weight for one epoch, and then you do it for the second epoch, third epoch, and then you average. So if P is the number of patterns in one epoch, you do that, you average over the year. Now, what is the effect of that? In some cases, it is advantageous to accumulate the weight correction terms for several patterns and make a single weight adjustment. This is equal to the average of the weight correction, just like this formula here. So why is this better? Because this formula has a smoothing effect because of the use of the average on the correction term. So when you average this, the weight update, you're sort of performing some smoothing effect, and this smoothing effect has shown to increase the chances of converging to a local minimum or a. Okay, the initial weights. Now we talked about, well, before we covered so we covered the pre-processing of the input pattern, the sequential versus batch mode. Now let's see what would we do with the initial weights. Initially, we said that we set them to random values, right? So the initial weight will influence whether the net or the network reaches a global or only a local minimum. If you remember, we've seen that on the weight space, the effect of when you select in one of the slides on the effect on selecting the initial weights. and then you can reach the global minimum very quickly or slower. So as I said, will influence whether the network reach a global of the error, and if so, how quickly it converges. So the values for the initial weight must not be too large. If these weights are too large, just like in this formula here, the initial weight, the initial input signals to each hidden or output unit will likely to fall in the region. So if this is very large, so you may fall in the region where the derivative of the sigmoid function has a very small value. So if this is very large, so you may be here, and then the saturation or the derivative of this function, f prime net, would be almost zero, would be very small. And in that case, in the weight adjustment, we will have zero here. So we reach saturation. We will not be able to update our weights. We're kind of stuck. We're stuck in a saturation region. Now that was when the weights are too large. Now also, if the initial weights are too small, the net input to a hidden or output unit will be close to zero. So if these weights are very small, then this would be also very small, so you'll be falling in this region here. And the f prime net will also be zero, so will be close to zero, which also causes extremely slow learning. So it'd be very small or close to zero. So the best way is to set the initial weights and the biases to random numbers between minus 0.5 and 0.5, or between -1 or 1. And the values can be, for the initial weight, as we've seen in one of the cases or slides before, they can be positive or negative, because after the final training, they may also be positive or negative. So the same thing for the initial weight. So memorization now versus generalization. How long are you going to train the network? So you have a training data set. You do it for 1 epoch, 2 epochs, 3 epochs. How many epochs are you going to do it for, or do your training for? So since the usual motivation for applying a backpropagation is to achieve a balance between memorization and generalization, it is not necessarily advantageous to continue training until the error actually reaches a minimum. So meaning that if you train too much, if you train with a large number of epochs, you may not allow the network, the multilayer perceptron, to generalize. It will memorize. So there is a rule or a rule of thumb on how to stop this this training, or when to stop this training. So you use, in this case, 2 disjoint sets of data during your training. So the ones that you use for training, and another subset called training testing or validation set. And weight adjustments are based on the training pattern. However, at intervals during the training, so every time, for example, every epoch, you compute the error using your validation set. And as long as the error for the validation set decreases, you continue training. But then when the error begins to increase, the network is starting to memorize the training patterns too much, too specifically, and then it starts losing its ability to generalize. And at this point, training should be terminated. So in short, this figure illustrates the whole thing. So if this is your error, this is your training time, or the number of epochs. So for example, you do your training for 1 epoch, you find that the error dropped here, you do it for another epoch, you train here, and so on. But then if you keep training for a long time, for a large number of epochs with this training set, and then you reach zero, you're just allowing the network to memorize. You're not allowing it to generalize. So what you do, you take your validation set, and then you see, oh, okay, my training error has decreased. Okay, let me check with the validation set. Okay, it is decreases. I keep training. And then the same thing, I test my validation set. It is decreasing. I keep training and so on. But then here you see that after a number of epochs, your error starts to, your error for the validation set starts increasing. In this case, you stop training. This is the best balance between memorization and generalization. So this is called the early stopping rule. Now, another variant of the backpropagation is backpropagation with momentum. And in this case, the weight change. So when you change your weight, you do it in a direction that is a combination of the current gradient and the previous gradient. So what you do, so you had your delta W on how to change the weights between node I and J. So we used to have a learning rate times the delta, that we backpropagate, times the input pattern, right? So in this case, we add another term, a momentum term, if you want to call it this way. Momentum can be added, so weights tend to change more quickly if changing in the same directions for several training cycles. So you, first of all, you have this momentum factor, which ranges between 0 and 1. And when subsequent changes are in the same direction, increase the rate. So meaning that if they change in the same direction, this term is going to increase, and then you have a bigger change in the weights. But then when the subsequent changes are going in opposite direction, so this rate decreases. This is a figure, this figure explains how it is, how it works. So you have, this is your, the new weight, which are equal to the old weight plus the plus alpha times the learning the delta learning rate alpha times delta times your input. So this is the weight update equation that we've seen. We add a mu delta W, which is the momentum term. And then basically what we do is, if we're moving along the same direction, this will increase. This will increase. And then if we're moving in the opposite direction, this would decrease. And then the same thing for the case. So this was for the weights between the hidden layers and the output layers. The same thing for the weights for the input layer and the hidden layer. So in this case, we have the V things, the V weights, and also we have the momentum term also for this. Backpropagation with an adaptive learning rate. If you remember, this was our steps when we did the backpropagation. And then this was the delta K that we feed to and we use to update our weights. But then we used to have this alpha constant. Now with the adaptive learning rate, we want to change it so that it is done adaptively. What does it mean? So we vary the learning rate during training. We accelerate the learning, accelerating learning slowly if all is well. So if the error is decreasing, we accelerate the learning. We'll make this alpha big or large. But then when the error is increasing, we reduce this alpha. We reduce it quickly if things go unstable. So if the error is decreasing, we decrease the alpha, meaning that our alpha, we change it at every time we do the update, the weight update. And then if the error is 0, we don't do anything. But then if it's decreasing for the last few epochs, we add another term to accelerate it. So if A is 0.1, we add a term to it. Now, if the error is increasing, because B is equal to 0.5, so this becomes 0.5. So we're reducing the learning rate. Now, this is you can do again the backpropagation with neural with the multi-layer perceptron and so on with the MATLAB and Simulink. So this is your input pattern. This is your summation to sum up. This is your bias, the net activation, the activation function, and so on. And then you can do a lot of things, but then it's easier now to do it with, you can choose to do it with MATLAB, but also it's easier to do it with TensorFlow or PyTorch. I have on my slides some an appendix to for some mathematical derivations, but I won't cover them here because we're just focusing on the concepts. And then also here are some suggested references. So this is Fawcett's Fundamental of Neural Networks. It's an old book, but it is quite good actually. It's very simple to understand the concepts. Also, there are some other references. Thank you.